everything humanity has ever observed, measured, and called the universe may be only 0.0000001% of the reality existing right now. The shocking truth is beyond that cosmic horizon. There may be trillions of galaxies, hidden regions of space, or even other universes we can never reach. Before we go further, like and subscribe, because what lies beyond the observable universe may be the biggest question science can never fully answer. Get ready? We begin. The Hubble Space Telescope, the James Webb Space Telescope, those staggering, color-drenched images of spiral galaxies, arms of stars sweeping outward like slow cosmic storms, frozen in light across millions of years. Most people look at those images and feel something close to certainty. The universe is vast. Yes, but science has seen it, mapped it, named it. There's a quiet confidence embedded in every textbook, every museum poster, every documentary that opens with a slow zoom through a field of galaxies. We know what's out there. That confidence is a trap, not a malicious one, not a failure of science, just the most natural illusion in the world, the belief that what we can see is what there is. What we call the observable universe is a sphere with a radius of 46.5 billion light years. That number gets thrown around a lot. It sounds enormous, and it is. But the number itself is almost designed to mislead, because it doesn't mean what most people assume it means. It is not the size of the universe. Read that again slowly. 46.5 billion light years is not a measurement of how big the universe is. It is a measurement of how far light has been able to travel in all directions from our vantage point since the Big Bang, 13.8 billion years ago, accounting for the expansion of space during that entire journey. It's a time limit dressed up as a distance, a cosmic horizon built not from walls or edges, but from the simple, brutal fact that light moves at a finite speed, and the universe has only been around for a finite amount of time. The boundary has a name, the cosmic microwave background, the CMB. It's the faint afterglow of radiation, released when the universe was just 380,000 years old, the moment the cosmos cooled enough for atoms to form and light to finally travel freely. Before that moment, the universe was so hot and dense that light couldn't move at all. Everything was opaque, a plasma fog with no transparency. The CMB is the oldest light we can detect. It is, quite literally, the farthest back we can see, not the edge of the universe, the edge of our view. Think about standing in the middle of the ocean on a foggy morning, thick sea fog, rolling in from every direction. Your visible horizon is maybe a few hundred feet. You can see the water around you, the swells, the color of the surface. And if you'd never been on open water before, if this were your entire frame of reference, you might be forgiven for thinking that the ocean ends where the fog begins. But it doesn't. Beyond the fog, the water continues. Waves still break, currents still run. Storms are forming somewhere you can't see, and they don't care that you can't see them. The fog is not a wall. It's a limit of information, your information, not the oceans. That's what the observable universe is. 46.5 billion light years of fog. Not a void, not nothing. A barrier of time and light, beyond which reality continues unobserved, unconfirmed by us, but not absent. On the other side of that boundary, the laws of physics don't stop. Space doesn't stop. Whatever is out there and everything we understand about cosmology suggests there's an enormous amount it's not waiting for our permission to exist. And yet, look at what we've accomplished within our fog-bound bubble. NASA and the European Space Agency, analyzing data from surveys like the 2016 Hubble Deep Field Study, led by Christopher Consolis and his team, estimated that the observable universe contains approximately 2 trillion galaxies. 2 trillion. Each galaxy itself home to hundreds of billions of stars on average. The Milky Way alone, our galaxy, Our neighborhood contains somewhere between 100 billion and 400 billion stars. Every single one of them a sun, many with planets, as 2 trillion galaxies. That's the image. That's the scale of what we've managed to glimpse from inside our bubble. It sounds complete. It sounds like everything. It sounds like the front yard of a house is the entire property. But that's exactly the illusion that the front yard is all there is, because it's all we've ever seen. The rest of the house, the backyard, the surrounding land, it exists. We just haven't seen the front door, let alone walk through it. And here's the part that should stop you cold. The physics strongly suggests we never will. This is where the comfortable narrative of science map the cosmos starts to quietly collapse. Every mosaic image of deep space, every galaxy catalog, every three-dimensional map of large-scale cosmic structure, all of it. Every single data point humanity has ever collected about the universe comes from inside this 46.5 billion light-year sphere. We have never received a single photon of information from outside it, not one. And we never will not, because our instruments aren't sensitive enough. But because the light from beyond that boundary hasn't had time to reach us yet. Some of it is traveling toward us right now. Photons launched billions of years ago from galaxies so far away that the universe itself has expanded beneath them as they travel. They're on their way. But the universe is also expanding faster than some of that light can cross the remaining distance. Some of those signals will never arrive. The boundary isn't static, it's dynamic. And in some directions, it's losing ground. What lies beyond the observable universe isn't mystery in the poetic sense. It's a hard, physical fact of inaccessibility, and the clearest signal of just how real that inaccessibility is. The oldest light we can detect, the CMB, that 380,000-year-old afterglow, marks the absolute limit of our look-back horizon. We cannot see earlier. We cannot see further. That's the wall, not the universe's wall, ours. If the universe humanity has ever known is just a small bubble inside a reality, far larger, possibly infinitely larger, then every cosmic map we've ever drawn is a map of what exactly NASA has photographed over 2 trillion galaxies. And yes, that sounds staggering until you realize it's still just the front yard of a house we've never seen the full face of. But the strangeness doesn't stop at what the universe is hiding from us. The geometry of space itself is whispering something far more unsettling, something the mathematics can no longer ignore. Light is the most trustworthy thing in the universe. That's the assumption, and it runs so deep, most people never question it. Sunlight takes 8 minutes to travel from the surface of the sun to your eyes. That's close enough to feel like now. The light from Proxima Centauri, our nearest stellar neighbor, takes 4.2 years, still manageable in cosmic terms. We look up at the night sky, we see stars, and somewhere in the back of our minds, we believe we're seeing the universe, the actual universe, the current one, the real one. Light carries information. Information is truth. Therefore, what we see is what is. Except it isn't, not even close. Point a telescope at a galaxy 10 billion light years away. You're looking at it right now, or what feels like right now. What you're actually seeing is that galaxy as it existed 10 billion years ago. The light entering your lens left its source when the universe was less than 4 billion years old. Earth didn't exist yet. The sun hadn't formed. Life, chemistry, planets, none of it. And that light has been traveling through an expanding universe ever since, stretching, shifting, finally arriving at a mirror or a detector after a journey no human timeline can meaningfully hold. So where is that galaxy now? What does it look like today in the actual present moment, the one you and I are sharing right now? Has it collided with a neighbor? Has it dimmed, scattered, transformed into something unrecognizable? Did it survive at all? We don't know. We will never know. That information does not exist for us. Not because it's been lost, but because the light carrying it hasn't arrived yet, and in many cases, it never will. This is the collapse that takes a moment to fully land. Every telescope humanity has ever built, from Galileo's first crude tube aimed at Jupiter's moons, to Hubble floating in low Earth orbit, to the James Webb Space Telescope unfurled 1.5 million kilometers from Earth at the second Lagrange point, none of them are observation instruments in the way we intuitively mean. They don't show us the universe. They show us the universe's past. They are, without exception, time machines pointed backward. The further they look, the further back in time they reach. No one is observing the present-day universe. Not astronomers in Arizona, not ESA scientists in Madrid, not the most sophisticated array of radio telescopes on the planet. No one. The present-day universe, as a coherent, observable object, simply does not exist for any single vantage point within it. Every data point, every spectrum, every galaxy redshift measurement, all of it is historical record. Some of it ancient, beyond reckoning. Imagine standing in front of a mirror, but this mirror has a peculiar property. Instead of reflecting your current face, it shows you what you looked like 10 years ago. Same posture, same room, but a decade younger staring back. You'd notice the difference immediately. You touch your face, compare, feel the gap between the image and the reality. Now imagine you had no way to touch your face, no independent reference point, no way to verify which version was real. You'd have no choice but to trust the mirror, and the mirror would be lying to you faithfully every single day. That's what every telescope on Earth is doing, showing us a reflection that's years, millions of years, billions of years out of date, and we have no face to touch, no independent now to compare it against. We trust the image because it's all we have. The most extreme example of this came in 2024, when the James Webb Space Telescope confirmed the most distant galaxy ever observed, JADES-GS-SZ14-0. Let that name hold its weight for a second. JADES-GS-AZ14-0 existed just 290 million years after the Big Bang. The light captured by Webb's instruments had been traveling for over 13.5 billion years before it landed on a detector the size of a dining table, floating silently in the dark between Earth and the Sun. When that light left its source, our Sun was not yet a thought in the mathematics of the universe. Earth was not a possibility. The molecular cloud that would eventually collapse into our solar system didn't exist. The atoms that make up your body were locked inside stars that hadn't been born yet, and we call seeing it observation. You might be thinking, at least we're still seeing it. Ancient light is still light, still real information. Fair point, and yes, technically, it is. But consider what you're actually claiming when you call that observation. What you see is a ghost, a signal from an entity that is now 13.5 billion years older than the image it sent. That galaxy, if it still exists in any recognizable form, has had 13.5 billion years of evolution, collision, star formation, star death, and transformation, none of which we have any access to. What we call seeing, JADES-GS-Z14-0, is the equivalent of finding a photograph of someone taken at birth and calling it a portrait of who they are today. Does that count as observation? Or is it something more like forensic reconstruction, piecing together what was from the evidence it left behind? There's actually a more honest name for what astronomers do. Observing the universe makes it sound like watching a live feed. It isn't. It's archaeology, cosmic light. Archaeology, the careful excavation of photons that are relics of a universe that no longer looks the way they describe. Every deep field image from Hubble, every infrared scan from Webb, every radio map from the Very Large Array is a dig site. The astronomers are not stargazers. They are, in the most literal sense, cosmic archaeologists, brushing dust off the luminous remains of a universe that has long since moved on. Which raises an uncomfortable question about everything built on top of those observations. Every model, every theory, every confident claim about what the universe contains. Yet even within all that ancient chaos, the universe obeys a rule so strange it cannot be coincidence, a perfection that mathematicians have no better word for than absurd. In physics, nothing sits perfectly still. Nothing balances exactly. A pendulum swings left, then right, never stopping precisely at center. Planetary orbits are ellipses, not circles slightly stretched, slightly off. Always with some eccentricity. Temperatures fluctuate with seasons, with altitude, with ocean currents. Even the fundamental constants of nature, when measured with enough precision, carry error bars, uncertainty ranges. The fingerprints of a universe that operates in approximations rather than absolutes. This is not a flaw. It's the texture of reality. Perfect equilibrium, in nature, is almost always a fiction or a trap, which makes what cosmologists discovered about the shape of the universe so deeply, profoundly strange. When physicists measure the total energy-matter density of the universe and compare it to what's called the critical density, the exact amount needed to produce a geometrically flat universe, they get a ratio. That ratio has a name, omega, and its value, measured with every instrument we have, refined across decades of increasingly precise observation, is 1.000. 1, exactly 1, flat, perfect. Not approximately flat, not flat within a comfortable margin that allows for some underlying curve we're too small to detect. The measurements keep coming back to 1 with a precision that has no business existing in a universe governed by the kind of chaotic initial conditions the Big Bang implies. A flat universe means parallel lines stay parallel forever. Light beams that start out side by side never converge, never diverge. The geometry of space on the largest scales is Euclidean. The same geometry you learned in high school, the one that works on a flat piece of paper, and the universe, across 46.5 billion light-years of observable volume, appears to obey it exactly. Now, here's where the strangeness becomes a genuine crisis. Omega equals 1 is not a stable resting state. It is, in the language of dynamical systems, an unstable equilibrium, the kind that exists in theory, but collapses the instant anything nudges it. Picture a perfectly round ball balanced on the very tip of a needle. Mathematically, that's a valid position. In practice, any infinitesimal vibration, a breath of air, a passing truck a block away sends the ball rolling off in one direction or another. The longer you wait, the further from the tip it rolls. Deviation compounds. The same principle applies to omega. If the early universe had a density even slightly above 1, gravity would have dominated, the expansion would have reversed, and the cosmos would have collapsed back on itself in a big crunch long before a single star could form. If the density had been even slightly below 1, the expansion would have run away so fast that matter could never have clumped together. No galaxies, no stars, no planets, no anything. Just a thin, cold, featureless gas spreading forever into an infinite dark. The window between those two outcomes is not wide. It is extraordinarily, almost insultingly, narrow. At the Planck time, 10 to the power of negative 43 seconds after the Big Bang, the earliest moment at which our current physics can say anything meaningful about the universe. Omega had to equal 1 to a precision of 1 part in 10 to the power of 62. 1 part in 10 to the 62. To feel the weight of that number 10 to the 62 is larger than the total count of atoms in the entire observable universe. If you took every proton, every neutron, every electron in every star in every one of those 2 trillion galaxies, added them all up, and wrote that number down, it would still be smaller than 10 to the 62. The precision required is finer than 1 atom out of all the atoms that exist. Imagine firing an arrow from the eastern coast of the United States, aiming at a target on the western coast. Not a bullseye, not a circle, a target 1 atom wide, and hitting it. Dead center, not once every single day, for 13.8 billion years in a row without a single miss. That is the level of precision baked into the initial conditions of this universe. That is what omega equals 1 actually means when you follow the mathematics back to the beginning. If that number had been off not by much, not by anything a human scale could detect, just by a fraction so small it has no name in ordinary language, you would not exist. Not in the sense of conditions would have been difficult, in the sense of no you, no me, no Earth, no Sun, no Milky Way, no periodic table of elements, no chemistry, no time long enough for evolution to stumble toward consciousness. The entire history of everything that has ever lived or thought or wondered would have been erased before the first second of cosmic time ran out. So what chose that number? What mechanism? What process? What initial condition produced a ratio so precise it strains the concept of coincidence past its breaking point? This isn't a question with an easy answer. It isn't a question physicists wave away. It sits at the center of modern cosmology like a splinter, and every model built to explain the universe has to reckon with it. Physicists call this the flatness problem, which, as names go, is almost comically understated. It sounds like something an urban planning committee might discuss over bad coffee, a minor issue of civic geometry, not the most unsettling fine-tuning puzzle in the history of science. But the name stuck. So here we are, calling one of the deepest mysteries of existence something that sounds like a complaint about road infrastructure. The flatness problem is not a problem of measurement. The instruments aren't broken. The math isn't wrong. The problem is that the universe appears to have started in a state of almost impossible precision, and nothing in the standard Big Bang model explains why. The equations don't produce it naturally. It has to be assumed, inserted as an initial condition, accepted as a given. And science is deeply uncomfortable with coincidences it can't explain. And the weight of that discomfort gets heavier the longer you sit with it. Because this isn't a rounding error. This isn't a measurement artifact. This is the universe itself arriving at a configuration so finely tuned that the natural response, the honest response, is to ask whether something produced it deliberately, or whether there's a mechanism we haven't found yet that makes this precision inevitable. The troubling answer, the one physics has reluctantly arrived at, is not the question itself. And the answer, when it finally came, turned out to be something that pushes the vast majority of the real universe permanently beyond our reach. Stand outside on flat ground and look at the horizon. The land stretches away, level in every direction. And if you didn't already know better, if no one had ever told you, if no satellite image existed, if the concept of a globe had never been proposed, you might reasonably conclude that the Earth is flat. The local evidence strongly supports it. The ground under your feet is flat. The horizon is flat. Every direction looks the same. We know this is an illusion. Of course, the Earth is round, roughly spherical, slightly oblate at the poles, and the reason the ground looks flat is simply that the planet is vastly larger than the slice of it visible from any single standing point. The curvature exists. We just can't see it from where we're standing. This is not a minor caveat. It's the exact cognitive trap that cosmology has been wrestling with for decades. The observable universe looks flat. Omega equals 1. The geometry checks out. Parallel lines stay parallel. No curvature detectable in any direction. But here is what the data actually permits. If you read it carefully, flatness within our observable bubble does not rule out curvature in the full universe. It only rules out curvature with a radius smaller than our observational horizon. If the total universe is curved positive curvature, like the surface of an enormous sphere, or negative curvature, like a vast saddle shape extending in every direction, but the radius of that curvature is larger than 46.5 billion light years, then from inside our observable region, it would look perfectly flat. We would have no way to tell the difference. None. The 2018 data release from the Planck satellite, the most precise map of the cosmic microwave background ever produced, measured omega as 1.0007, plus or minus 0.0019. Within measurement, uncertainty, perfectly flat. That result is extraordinary. It's also not as airtight as it sounds. That error margin of plus or minus 0.0019 is small, but it is not zero. And within that window lives the possibility of a universe with a gentle, real curvature. One that simply has a radius of curvature so enormous that the 46.5 billion light-year sphere we inhabit is too small a sample to register it. The data doesn't prove flatness. It proves that any curvature, if it exists, is too large scale for us to measure from our current position. The distinction matters enormously. One conclusion says the universe is flat. The other says we can't rule out that it isn't. We just can't see far enough to know. Think about an ant on a basketball. From the ant's perspective, the surface is flat. It has no way to perceive the curvature. Its body is too small, its range of movement too limited, and the ball too large relative to its size. If that ant were a scientist, and it measured the geometry of the surface beneath its feet with the most precise instruments its civilization could build, every measurement would come back flat, Euclidean, no curvature detected. Now scale that up. Replace the ant with all of human civilization. Replace the basketball with a sphere so large that our entire observable universe, all 46.5 billion light-years of radius, is smaller than a single atom on its surface. The ant's instruments would never detect the curvature. Not because the instruments are bad, because the sample size is cosmically, fundamentally insufficient. That is not a hypothetical. That is a live possibility in current cosmology. And no observation we can make from inside our light bubble can rule it out. This is where the logic starts to fold back on itself in an uncomfortable way. If the universe is genuinely, truly flat, not just locally flat, but flat across its full extent, then it is almost certainly infinite. An infinite flat universe has no center, no edge, no boundary, just space continuing in every direction without limit. That's one option, and it carries its own staggering implications. But if the universe has any curvature at all, even a tiny positive curvature, it could be finite, but unbounded, like the surface of a sphere, finite in total volume, but with no edge you could ever reach or point to. And if it has negative curvature, the geometry opens outward, and the universe is again likely infinite, but shaped like a vast hyperbolic surface, something like an infinite saddle. Three radically different architectures for all of reality, and from where we stand, we cannot distinguish between them. The flatness we measure is consistent with all three, as long as the scale is large enough. We are, in a very precise sense, trying to deduce the shape of an ocean from a single bucket of water. The bucket is full, the measurements are accurate, the water is real, but no analysis of what's in the bucket can tell you whether the ocean is round, oval, infinite, or shaped like something that has no name in human geometry. Confidence in science is usually a virtue, but confidence about the global shape of the universe, built on observations confined to a bubble that may represent a vanishingly small fraction of what exists, that particular confidence might be the most expensive intellectual mistake we've ever made. And here's the deeper cut: the flatness we observe. The omega equals 1 result that started this whole chain of reasoning is itself a clue pointing towards something enormous and invisible, something that happened before our observable record begins, something that would explain both the flatness and another cosmic puzzle: why the universe looks almost identical in every direction, even in regions that, by the standard Big Bang model, could never have been in contact with each other. Both of those mysteries, the perfection of flatness, the uniformity of temperature, need a single explanation. And physics has one ready. It is bold to the point of nearly sounding insane, and it comes with a consequence that permanently seals off most of what's real from anything we could ever see or touch: the Big Bang. Everyone knows the story. The universe began from an extraordinarily small, extraordinarily hot point, and it expanded outward from there. 13.8 billion years of history, all traced back to a single origin. It's a clean narrative, almost satisfying in its simplicity. Start small, grow big. Here we are. Linear, comprehensible. The kind of origin story that fits on a museum wall, except that's not what happened. Not exactly. Not even close. Between 10 to the power of negative 36 seconds and 10 to the power of negative 32 seconds after the Big Bang, a window of time so short it makes a nanosecond look like a geological era, the universe underwent something that the standard expansion story doesn't prepare you for at all. It inflated, not expanded. Inflated, exponentially. The technical term is cosmic inflation, and the scale of what happened during those instants staggers every attempt to describe it honestly. The universe grew by a factor of at least 10 to the power of 26. In some models, significantly more. That number deserves a moment of silence before we move past it. 10 to the 26 is not just large, it is a category of largeness that breaks the part of the brain responsible for intuitive scale. Consider a single hydrogen atom, the smallest, simplest atom in existence, a proton with an electron in orbit, about 1/10,000,000th of a meter across. If that hydrogen atom underwent inflation and grew by a factor of 10 to the 26, its final size would exceed the diameter of the entire observable universe as we know it today. One atom. Bigger than everything we've ever seen or measured in any direction, across 46.5 billion light years. That is what happened to the early universe, not to one atom, to all of it. Hold a grain of sand between your fingers. Feel its weight? Almost nothing. A tiny fragment of silicon, maybe a millimeter across. Now imagine that in less than 1/1,000,000th of a second, that grain of sand doesn't just grow, it erupts. Not because the matter inside it is moving outward, but because the space between every point within it is stretching, multiplying, expanding faster than any speed limit in physics applies. And at the end of that eruption, it's larger than the Milky Way. That is the violence of what we're describing, compressed into a time frame that has no analogy in human experience. The theory of cosmic inflation was first proposed in 1980 by Alan Guth, a physicist at MIT who was trying to solve exactly the problems we've been examining: the flatness problem and a related puzzle called the horizon problem, which asks why the cosmic microwave background has almost exactly the same temperature in every direction, even in regions that, according to standard Big Bang timelines, could never have been in causal contact with each other. They're too far apart. Light couldn't have traveled between them. So how did they know to be the same temperature? Inflation solves both problems in one move. If the very early universe was an extraordinarily small, causally connected region, small enough that temperature could equalize and then inflated exponentially. That tiny uniform patch would be stretched across a volume far larger than our observable universe today. The temperature uniformity we see in the CMB isn't a coincidence. It's a relic of how small and connected everything was before inflation ran. And the flatness. Any curvature that existed before inflation got stretched so thin across such a vast scale that it became undetectable. Same reason a balloon looks flat: when you inflate it enough, the curvature is real, but the radius has grown too large to measure locally. The indirect evidence for inflation is embedded in the CMB itself, specifically in what physicists call the nearly scale-invariant spectrum of primordial density. Fluctuations, tiny variations in the density of the early universe that seeded the formation of galaxies. Inflation predicts a very specific pattern for these fluctuations, nearly the same amplitude at all scales, with a slight tilt. The measurements, refined across multiple satellite missions, including WMAP and the Planck satellite, match that prediction with remarkable precision. Inflation wasn't confirmed by seeing it happen. It was confirmed by reading the fingerprints it left behind. You might be raising an eyebrow right now. If the universe expanded faster than light during inflation, doesn't that break physics? Doesn't Einstein's special relativity say nothing can exceed the speed of light? It does, but there's a distinction that matters enormously here. Special relativity prohibits objects from moving through space faster than light. Inflation is not objects moving through space. Inflation is space itself expanding. Those are not the same thing. No particle, no photon, no piece of matter violated any speed limit. The space between points simply grew, and nothing in general relativity forbids that. In fact, the mathematics of general relativity is precisely what describes it. The physics isn't broken. Only our intuition is broken, because our intuition was built on a planet where space behaves itself. Cosmic inflation, as a name, carries a faint air of economics about it. It sounds like something that happens to grocery prices, not to the geometry of the cosmos. No one has replaced the term, probably because everyone in the field got used to it. And also, if you think about it, both kinds of inflation share at least one thing in common. They make everything much, much larger than you expected, and the consequences are someone else's problem. But inflation doesn't only explain flatness and temperature uniformity. It comes with a receipt, a cost, something it takes from us permanently, in exchange for the universe it gave us. And that cost is the subject of everything that follows, because inflation didn't just solve the puzzles, it hid the evidence. But inflation doesn't just explain flatness. It left behind a bill we will be paying forever. When you smooth out a crumpled piece of paper, you stretch it flat, work out every wrinkle and fold, press it down until the surface is even. The papers change smoother, more uniform, but nothing is missing. You still have the whole sheet. Every square inch that existed before the flattening still exists after it. The process costs you nothing except effort. Cosmic inflation is nothing like that. When space expanded exponentially in the first fractions of the first second of existence, it didn't simply smooth things out while leaving everything intact. It pushed regions of space regions that were, at the moment of inflation, part of the same causally connected universe as everything else so far away, so fast, that the causal connection was permanently severed. Not temporarily interrupted, not weakened, severed, the way you can't uncut a wire. The concept at the center of this is the causal horizon, the boundary beyond which no signal, no light, no information of any kind can ever reach us. Because the space between here and there is expanding faster than light can cross it. Inside the causal horizon, physics can connect things, information can travel, cause can produce effect. Outside it, those relationships simply don't exist. There is no channel. There is no path. there is nothing. And inflation, in the process of flattening the universe and solving the problems of the early cosmos, threw an enormous portion of reality, possibly the vast majority of it, permanently across that line. That portion didn't disappear. This is important. Whatever lies beyond our causal horizon is not gone. It's still there, still occupying space, still evolving, still subject to gravity and time and the forces of physics. Stars are likely forming in those regions right now. Galaxies are spinning. If there are planets, processes are happening on them that we will never know about. The universe beyond our causal horizon is not empty. It is simply inaccessible, not as a matter of current technology, but as a matter of fundamental physical law. Imagine you're in the middle of a phone call, the signal is clear, the conversation is flowing, and then, not because the other person hung up, not because the phone broke, not because of any failure on either end, the carrier simply stops being able to bridge the distance. The other person is still there, still talking, presumably, but every word they say from that moment forward is traveling toward you through a medium that is stretching faster than the sound can cross it. The signal disperses into nothing. The call is over, not because either party stopped existing, because the space between you grew too large for connection to survive. That is what inflation did to the portions of the universe. It pushed past our causal horizon. Not destruction, disconnection, permanent, irrevocable, physics-enforced disconnection. Our causal horizon, the boundary defined by the distance light emitted at the moment of the Big Bang, could have traveled since then. Accounting for the expansion of space, sits at approximately 46.5 billion light years. That's the observable universe. Everything inside that sphere is, at least in principle, something we could detect, measure, receive a signal from. Everything outside it was pushed there by inflation and has been receding ever since. Right now, as you read this, that portion of the universe is happening. Somewhere beyond 46.5 billion light years in every direction. Space is not empty. Events are unfolding. Whatever processes the physics of our universe permits are playing out in real time, in a region we cannot observe, cannot contact, cannot verify, and cannot reach, not with a faster ship, not with a more powerful telescope, not with any technology conceivable under the laws of physics as we understand them. The barrier is not engineering. The barrier is causality itself. Does that land really land? Because it should feel like something. There is a universe happening right now that we are permanently locked out of, not metaphorically, not as a poetic way of describing scientific limitation. Literally, the expansion of space, seeded by inflation and now driven by dark energy, has built a wall around our observable region, not made of matter, not made of force, made of the structure of space-time itself, and nothing crosses it in either direction. Technically, of course, we are not alone in the universe. We are simply alone in the portion of the universe we can access. The distinction, unfortunately, does nothing to make the night feel less cold. So how much is on the other side of that causal wall? How much reality did inflation push past the line? The number coming next is the kind that requires you to sit down first. The observable universe contains approximately 2 trillion galaxies. 2 trillion, each one a gravitational system containing, on average, somewhere between 100 billion and 400 billion stars. The Milky Way sits comfortably in that range. Our galaxy alone, just one of 2 trillion, holds enough suns to make the concept of counting them feel faintly absurd. Most people, when they encounter that number, experience something like awe. 2 trillion galaxies. It sounds complete. It sounds like everything. It sounds, if you're being honest, like more than enough universe for anyone. It isn't even close to the beginning. Based on inflationary cosmology models, the same framework that explains the flatness problem and the uniformity of the cosmic microwave background. The total universe, meaning the full extent of space that actually exists beyond our observable bubble, must be larger than our observable region by a factor of at least 251 in diameter. That's the conservative lower bound derived from the mathematics of inflation. Some models place the figure vastly higher. Others suggest the total universe may be genuinely, literally infinite. 251 times larger in diameter sounds manageable until you remember that volume scales with the cube of the radius. A sphere 251 times wider in diameter is not 251 times larger in volume. It is 251 cubed times larger, approximately 15.8 million times the volume. 15.8 million observable universes, packed side by side, would fill the volume of the total universe under the most conservative inflationary estimate. 15.8 million times 2 trillion galaxies. That product is a number with somewhere between 25 and 30 digits. The English language has names for large numbers up to a point million, billion, trillion, quadrillion, quintillion, and then the names run out long before the number does. There is no common word for what you get when you multiply 2 trillion by 15.8 million. It lives in a region of arithmetic that human language never bothered to map because nothing in daily experience ever required it. The analogy that comes closest to capturing the scale, take the entire observable universe, all 46.5 billion light years of radius, all 2 trillion galaxies, everything humanity has ever observed or measured or theorized about, and shrink it down to a single grain of sand. One grain sitting in your palm. Now the total universe, at the conservative 251 diameter estimate, would be larger than the entire Pacific Ocean filled to the brim with grains of sand that same size. Every grain in that ocean representing a full observable universe's worth of galaxies, stars, and space. And 251 times is the floor. The minimum, the number the mathematics produces when you apply the most restrained version of inflationary models. MIT physicist Max Tegmark, in work examining the implications of inflationary cosmology, has argued that the total universe could plausibly be larger than our observable region by a factor of at least 10 to the power of 23 100 sextillion times. That's not a fringe estimate. That's what the physics, taken seriously, actually implies. If that's true, if there are galaxies beyond our horizon, numbering in the tens of sextillions, operating under the same gravitational laws, the same nuclear physics, the same electromagnetic forces, evolving through the same stellar life cycles, then what exactly is the word universe describing when we use it? What are the maps describing? What is the catalog of 2 trillion galaxies? Actually, a catalog of. The honest answer is a neighborhood, not even a large one. A small corner of something so vast that calling it the universe is a bit like calling your zip code the world. The history of astronomy is, at its core, a series of humiliations delivered gently over centuries. First, we learned Earth is not the center of the solar system. Then we learned the sun is not the center of the galaxy. It's an ordinary star in an outer spiral arm, nothing special about its position. Then we learned the Milky Way is not the center of anything, just one among 2 trillion other galaxies distributed throughout the observable volume. Each step stripped away another layer of assumed centrality, another implicit belief that where we are is somehow the important part. And now, this. It turns out the entire observable universe, all 2 trillion galaxies, all the deep field images, all the spectroscopic surveys, every data point ever collected by every telescope ever built, may itself be a fragment, a statistically insignificant fragment of a total reality so much larger that our entire observable bubble is to the full universe what a single atom is to the Pacific Ocean. Humility, it seems, is a lesson the cosmos never tires of teaching. All of that vast space out there, every region beyond our causal horizon, presumably runs on the same physics as us. The same laws, the same constants, the same rules, at least in theory. But the question that cuts deeper, the one that keeps theoretical physicists awake, is a different one entirely. What if it doesn't? In physics, shared laws mean shared predictability. If two systems obey the same rules, you can understand one by studying the other. An electron on Earth carries a charge of approximately 1.6 times 10 to the power of -19 coulombs. An electron in a galaxy 10 billion light-years away carries the exact same charge. Its mass is identical. Its behavior in a magnetic field follows the same equations. The speed of light is the same there as it is here. The ratio of proton mass to electron mass doesn't change with address. This universality is not a minor observation. It's the entire foundation of physics as a discipline. If the laws varied from place to place, if an electron in Andromeda behaved differently from an electron in the Milky Way, the whole project of science as a tool for understanding the cosmos would collapse. We assume uniformity. We build everything on top of it. But here's the crack in that foundation that doesn't get discussed enough. The vast majority of the total universe lies beyond our cosmological event horizon, meaning that light emitted from those regions today will never reach us. Hasn't reached us yet. Never. The space between us and them is expanding faster than light can cross it. No signal, no photon, no gravitational wave, no information of any kind will ever make the journey. The connection is not slow, it is absent. The cosmological event horizon, distinct from the observable universe boundary, sits at approximately 16 billion light-years from us. Any galaxy currently located beyond that distance is, right now, receding faster than light. Not because it's moving through space quickly, but because the space itself between us and it is stretching faster than light can traverse it. Any light that galaxy emits today will never arrive here. Any signal we send today will never arrive there. That 16 billion light-year boundary is not the edge of what we can see. It's the edge of what we can ever affect or be affected by. From this moment forward, everything beyond 16 billion light-years is already causally in another world. So we are left with a strange and uncomfortable situation. We share a universe presumably with a number of galaxies, so large it has no name in the English language. We believe those galaxies follow the same physics. We believe electrons there have the same charge. Stars fuse hydrogen by the same process. Gravity falls off as the inverse square of distance, and space and time curve in response to mass and energy, just as they do in our local neighborhood. We believe all of this, but we cannot check. Not now. Not ever. The belief is theoretically motivated. The same inflation that produced our observable universe presumably produced the rest of it under the same conditions. So the same laws should apply. But presumably and should are not experimental confirmations. They're extrapolations, confident, well-reasoned extrapolations, but extrapolations nonetheless. The uniformity is theoretical. The isolation is physical. Think about a library, not a small one. A library containing hundreds of trillions of books, each one written in English, each one following the same grammar, the same syntax, the same rules of meaning. Imagine you know with near certainty that every book in that library is written in English because every book you've ever read has been in English and the same press printed them all. Now imagine every one of those books is locked in a separate sealed room, no windows, no doors, no way in or out, and the keys were discarded 13 billion years ago. You know what language they're written in. You've never read a single page of any of them. You never will. That is the relationship between us and the galaxies beyond our cosmological event horizon. We know the language. We've never read the text. We never will. The current cosmological event horizon places a hard limit, not a technological one, a physical one, on the universe we can meaningfully interact with. Any galaxy beyond 16 billion light-years is lost to us, not because our instruments are inadequate, but because the structure of space-time has already decided the matter. Dark energy, which we'll come to shortly, is accelerating the expansion continuously, which means that horizon isn't static. It's shrinking. In terms of what we can still exchange signals with, galaxies that are today just barely within reach are being pushed toward and past that boundary in cosmic time. You might want to push back at this point. At least we know those galaxies exist. At least the theory tells us they're there. That's something. Fair enough, it's not nothing. But consider what kind of knowing that actually is. Knowing without the ability to observe, knowing without the ability to verify, knowing that can never, under any circumstances, be tested by any experiment or measurement conceivable within the laws of physics. That kind of knowing has a different name in most fields of human inquiry. In science, it occupies an uncomfortable borderland that some physicists find deeply troubling and others find perfectly acceptable. We pride ourselves on having 2 trillion galaxies in our cosmic catalog. But those 2 trillion galaxies are like holding 2 trillion banknotes that can never be spent, never be seen directly, and whose very existence, beyond a theoretical inference, can never be confirmed. The wealthiest paupers in the cosmos, rich in universe, bankrupt in access. And if that's the situation within a universe governed by a single set of physical laws, if even the universe we theoretically share with those unreachable galaxies creates this level of radical isolation, then what happens when the question is not about distance, but about structure? What if space doesn't extend outward in straight lines at all, but folds back on itself, like an enormous donut, and the story of where the universe ends has to be rewritten from scratch? Most people picture the universe one of 2 ways. Either it stretches outward forever, it's infinite space in every direction, galaxies thinning out into an endless dark, or it's a kind of expanding bubble, a sphere growing larger with every passing moment. The Big Bang at its origin. Both images are intuitive, both feel geometrically honest, and both carry the same implicit assumption travel far enough in a straight line, and you either reach an edge or you never stop because there isn't one. Neither option leaves room for a third possibility, but mathematics does. Topology, the branch of mathematics concerned with the fundamental properties of space and shape. The study of what stays the same when you stretch or bend a surface without tearing it opens a door that pure intuition keeps closed. A space can be finite in total volume and simultaneously have no boundary whatsoever. No edge, no wall, no place where space simply stops and something else begins. The surface of a sphere is the most familiar example. Walk in any direction on a sphere and you never hit an edge, yet the total surface area is perfectly finite. There's no contradiction. The geometry just wraps. But topology offers something more subtle than a sphere, something that, when you understand it, reframes the entire question of what the universe's shape might be. A torus, the mathematical name for what, in 3 dimensions, resembles the surface of a donut. On a 2-dimensional torus, moving in one direction long enough doesn't bring you to an edge. It brings you back to where you started, from the other side. Left becomes right. Forward becomes behind. The space is closed, self-referential, and finite. But at no point does it have a boundary you could stand at and look over. In 3-dimensional space, a toroidal topology works the same way. Travel far enough east, and you approach from the west. Go far enough up, and you return from below. The universe wraps around itself in all 3 spatial dimensions, forming a closed geometry with no interior and no exterior, just space that connects back to itself, like a room where every wall is a doorway to the opposite wall. The analogy that makes this click faster than any equation Pac-Man: when Pac-Man moves off the left edge of the screen, he appears on the right. Move off the top, appear at the bottom. The screen looks flat, looks bounded, looks like it has 4 hard edges. But the geometry it's actually describing is toroidal, a closed surface where opposite edges are identified as the same point. There is no edge in the gameplay, only wrapping. The universe could be Pac-Man at cosmological scale. This is not a fringe idea born in a philosophy seminar. In 2003, Jean-Pierre Luminet and colleagues published a paper in Nature proposing a specific finite topology, the Poincaré dodecahedral space, as a potential explanation for certain anomalies observed in the large-scale structure of the cosmic microwave background. The CMB's power spectrum showed less fluctuation at the largest angular scales than standard infinite universe models predicted. One candidate explanation: a universe with a finite topology, where the largest possible wavelengths of fluctuation are cut off, because space wraps around before they can fully develop. The dodecahedral model fits certain features of the data. It was taken seriously by serious people. More recently, analysis of Planck satellite data published in 2022 continued to leave finite topology models open. Not confirmed, but not excluded. The door has not been closed. Now, hold the full weight of what this implies. If the universe wraps back on itself, if you traveled in a straight line long enough and returned to your starting point, then the light you're seeing from distant galaxies might not always be coming from distinct objects. Some of it could be coming from our own galaxy, from the Milky Way, from a direction that, in a wrapped geometry, eventually loops back to the source. We could be looking at ourselves and not know it. The Milky Way, at a different stage of its development, could have appeared in astronomical surveys conducted right now, cataloged as a distant galaxy at some vast redshift, assigned a name and a classification, studied for its spectral properties, and no one would have any way to recognize it. The light left billions of years ago. The galaxy in the image would look nothing like the one we currently inhabit. There would be no label, no fingerprint obvious enough to flag it. We might have photographed our own home from the outside, from billions of years in the past, and filed it under a catalog number without a second thought. In fact, theoretically, the farthest galaxy James Webb has ever captured, JADES-GS-ZE14-0, that record-holding object from 290 million years after the Big Bang could, in a topologically closed universe, be an ancestral image of the Milky Way itself, seen from the far side of a cosmic loop. Astronomers and family historians, it turns out, may be practicing the same profession. But why can't we just check if the universe wraps? Shouldn't there be some kind of signature, a repeated pattern in the sky? A copy of our galaxy visible in 2 different directions, something that gives the game away. There should be. And that's exactly what researchers have looked for. The answer to why we haven't found it yet is not disappointing. It's one of the most clarifying facts in all of cosmology, and it leads directly into what inflation actually did to the shape of everything. But the reason we cannot confirm this isn't a lack of telescopes. It's that inflation stretched those folds so far apart that we can no longer see the seams. To determine the shape of any surface, you need a vantage point large enough to take it all in. You cannot tell that Earth is round by standing in a Kansas wheat field. The curvature is real, but from ground level, in every direction, the horizon looks flat. It took the view from space the full disk of the planet visible at once to make the spherical shape undeniable. Scale of observation determines what shape becomes legible. This principle is not unique to Earth. It applies universally. The shape of any structure only becomes visible when your observation window is large enough relative to the structure itself, which means there is a precise and devastating reason why we cannot determine the topology of the universe from where we stand. And it has nothing to do with the quality of our instruments. Inflation stretched the universe by at least a factor of 10 to the 26. Whatever topology existed before inflation, whatever wraps, folds, or self-connections the space had, those features were not erased. They were dilated, pulled to scales so vastly larger than what inflation started with, that the distance required to complete one loop of a toroidal universe, the length you'd need to travel in a straight line before returning to your starting point, could now be tens of millions of times larger than the entire observable universe. Think about what that means in practice. If the universe is a torus, the topology is real, the wrapping is real, the self-connection is real, but the radius of that loop, the circumference of the cosmic donut, so to speak, may be so enormous that our 46.5 billion light-year bubble of observation sits somewhere deep inside a single cell of the topology, nowhere near the point where the space curves back on itself visibly. We are inside the fold, and the next fold is so far away that no signal from it has reached us, and none ever will. Imagine trying to measure the circumference of Earth by looking through a pinhole in a wall. Your eye is perfect, your instruments are precise, but the hole is a millimeter wide, and the feature you're trying to detect, the full arc of the planet, requires a field of view spanning thousands of miles. No improvement to your eyesight resolves the problem. The constraint is the hole, not the eye. That is the situation in cosmic topology. The causal horizon, our 46.5 billion light-year observational limit, is the pinhole. The topology of the full universe is the planetary arc. No telescope, no matter how powerful, can see around a corner that lies beyond the causal boundary. The limit is not engineering. It is physics, fundamental, non-negotiable, written into the structure of space-time by the speed of light and the age of the universe. Researchers have looked rigorously and specifically. The method is called a cosmic topology search, and it looks for what physicists call matching circles in the cosmic microwave background. If the universe has a finite topology smaller than the observable volume, light traveling around the cosmic loop would create pairs of circles in the CMB that have identical temperature patterns, like two photographs of the same landscape taken from the same angle. The Planck collaboration, working with the most detailed CMB maps ever produced, conducted this search systematically through 2015. They found no matching circles. But here is the critical qualification that rarely makes it into the popular summary: that null result only rules out topologies with a characteristic length smaller than the diameter of the observable universe. If the loop length is larger than our observable bubble, which inflation strongly suggests, it would be the matching circles would fall outside our observational horizon entirely. We would never see them. The search would return empty, and the topology could still be real. Not finding the evidence is not the same as finding it absent, especially when the search tool is physically limited by the very space it's searching inside. This is, without exaggeration, the only problem in the history of science where the correct answer and the incorrect answer produce exactly identical observational results from our position. A universe with a topology too large to detect looks, from the inside, completely identical to a universe with no topology at all. Every measurement comes out the same. Every map is indistinguishable. The scientist and the philosopher, for once, are standing at exactly the same blind spot. What makes this genuinely strange, not just philosophically uncomfortable, but physically strange, is that the question of the universe's topology is not a question about something distant or abstract. It's a question about the shape of the space you're sitting in right now, the room around you, the city outside, the sky above all of it embedded in a geometry whose global structure we cannot determine, not because we haven't tried, but because the universe has made the evidence physically inaccessible. We live inside a shape we cannot measure. We inhabit a structure we cannot fully describe. The home we have always lived in is the one thing we are least equipped to see clearly, because seeing it would require stepping outside it, and outside is exactly where causality won't let us go. But set the shape question aside for now, because the next question isn't about the size or geometry of one universe. It's about whether there's more than one. Inflation is easy to think of as an event, something that happened. It started, it ran, it ended the way a storm builds, peaks and breaks. The Big Bang itself gets treated the same way: a singular moment, a defined origin, the beginning of the story with a clear first page. Cosmology, when taught in textbooks, tends to present these things with the comfortable structure of a narrative: beginning, middle, ongoing, a line with a start. That picture is almost certainly wrong. The theory of eternal inflation developed through work by Andre Linde at Stanford and Alan Guth at MIT, building on the original inflationary framework from the early 1980s, describes something fundamentally different from a single inflation event that started and stopped. In the eternal inflation picture, the quantum field responsible for driving inflation does not decay uniformly across all of space at once. Quantum fluctuations are inherently random. In some regions, the inflaton field drops to a lower energy state, and inflation ends, producing what we'd recognize as a hot, dense environment that then evolves into a universe filled with matter and radiation, a Big Bang, a cosmos like ours. But in the surrounding regions, the field stays high, inflation continues. And because the exponential expansion of inflationary space generates new volume faster than local quantum fluctuations, can end inflation within it. The inflationary background never runs out of space to keep expanding. The inflation never stops. Not globally, not in the larger structure. It is, in the most literal mathematical sense, eternal, extending without end into the future, generating an ever-growing volume of exponentially expanding space, within which bubble universes nucleate and form constantly, each one a self-contained cosmos with its own Big Bang, its own history, its own internal physics. Our universe is one of those bubbles. The Big Bang that produced everything we've ever known, every galaxy, every atom, every moment of 13.8 billion years of cosmic history, was not the beginning of everything. It was the moment our bubble formed, the moment a region of inflationary space underwent a phase transition, dropped out of the inflating background, and began evolving as a distinct, causally closed universe. Outside our bubble, inflation was still running. It's almost certainly still running now. Other bubbles have formed since ours. Others are forming at this moment. The inflationary ocean doesn't care that we nucleated. It just keeps boiling. The analogy that captures the scale and structure an ocean with no shore and no bottom, perpetually at a rolling boil. Every bubble that rises from within it is a complete universe with its own geometry, its own laws, its own trajectory through time. Some bubbles are large. Some may be tiny by comparison. Some collapse almost immediately after forming. Others expand and evolve for hundreds of billions of years. Our universe is one bubble, currently 13.8 billion years into its expansion, floating in an inflationary medium that has no edge, no center, and no end in sight. The credentials behind this picture are not marginal. Alan Guth, Andre Linde, and Alexander Vilenkin, three of the architects of inflationary theory, have each, through different lines of mathematical reasoning, concluded that eternal inflation is not an exotic extension of the original idea, but rather its near inevitable consequence. If inflation happened at all, If the physics that produced the flatness and temperature uniformity we observe was real, then eternal inflation follows from the mathematics almost automatically. You don't add it as a separate assumption. It emerges from the equations. Which means if you accept inflation and the observational evidence strongly supports it, you get eternal inflation as part of the package. And eternal inflation means an infinite, ever-growing population of bubble universes, each one a cosmos, the vast majority of them forever beyond any possible contact with us. Now, let the logic cascade. If our universe is a bubble, one among an infinite number of bubbles, then the Big Bang was not the origin of existence. It was a local event. A phase transition in one corner of a larger structure that had no beginning. We can identify and will have no end. The concept of the origin of the universe, as usually meant, dissolves. There is no single origin. There are an infinite number of origins, each one a bubble nucleating in an ocean that was already there, that had already been there, that may have always been there in some form that current physics can't yet fully describe. The entire conceptual framework of where did everything come from needs to be rebuilt from the ground up. We spent centuries arguing about our position in the solar system, then our position in the galaxy, then the significance of our galaxy among others. And the cosmos kept answering the same way each time: you are not where you think you are. You are not as central as you assumed. The thing you thought was everything is just a part of something larger. And now, physics delivers the same verdict one more time. At the largest possible scale, you are a bubble, among infinitely many bubbles, in an ocean with no shore. Have a nice day. But the truly unsettling part isn't that we're a bubble. It's that the other bubbles may be running on entirely different rules. The speed of light is approximately 299,792,458 meters per second. The gravitational constant is 6.674 times 10 to the power of negative 11 cubic meters per kilogram per second squared. The mass of an electron is 9.109 times 10 to the power of negative 31 kilograms. These numbers sit in physics textbooks as though they were carved into the fabric of reality by something permanent and necessary, the fundamental constants. The parameters that define how the universe operates, the same everywhere, the same always. That assumption is so deep, it rarely gets examined. It feels less like a hypothesis and more like a background condition. The way the solidity of the ground feels less like a property worth noting and more like just the way things are. In the framework of eternal inflation, that assumption breaks. When a bubble universe forms, when a region of inflationary space undergoes a quantum phase transition and drops out of the inflating background, the quantum fields within that bubble settle into a ground state. In the language of quantum field theory, this is called the vacuum state, and it determines the physical constants that govern everything that happens inside the bubble afterward. The mass of particles, the strength of forces, the rate at which gravity operates, the energy scale at which nuclear reactions proceed. Crucially, the process by which quantum fields settle into their vacuum state is not deterministic. It's probabilistic, random. Different bubbles, nucleating in different regions of the inflationary background, will have their fields settle differently, and different vacuum states produce different physical constants, not slightly different, potentially radically, structurally, fundamentally different, different enough that the physics inside one bubble universe might bear almost no resemblance to the physics inside another. Consider what varying those constants actually means in practice. In a universe where the gravitational constant is significantly stronger, matter collapses into black holes almost immediately after forming no stable stars, no stellar fusion, no elements heavier than hydrogen, no chemistry, no planets. In a universe where the electron is heavier by even a modest factor, Electrons cannot maintain stable orbits around nuclei. Atoms, as we know them, cannot exist. Chemistry is impossible. And the entire molecular basis of life is gone before it starts. In a universe where the strong nuclear force is slightly weaker, protons and neutrons don't bind tightly enough to form stable nuclei heavier than hydrogen. No carbon, no oxygen, no periodic table worth mentioning. Change one number by enough, and the entire architecture of complexity collapses. Picture every state in the country operating not just under different traffic laws, but under different physics. In one state, gravity is twice as strong. Nothing with legs can walk. No structure more than a few feet tall can stand. In the neighboring state, light travels 10 times slower time. Perception and communication all work differently. In the state after that, atoms are fundamentally unstable. Matter as we know it dissolves within microseconds of forming. And you cannot cross the border. You are locked inside your state permanently, with no way to visit the others and no ability to even send a message across the line. That is the multiverse implied by eternal inflation, combined with the quantum landscape of possible vacuum states. And the landscape is not a small space of possibilities. String theory, the theoretical framework attempting to unify quantum mechanics and general relativity, predicts approximately 10 to the power of 500 distinct vacuum configurations, each corresponding to a different set of physical constants. 10 to the 500. That number is so immense that even describing it in terms of other large numbers is difficult. The total number of atoms in the observable universe is roughly 10 to the 80. 10 to the 500 is incomparably larger. A space of possibilities so vast that almost every conceivable configuration of physics gets represented somewhere across the multiverse. The string landscape, as physicists call it, combined with eternal inflation's mechanism for populating it, produces a picture where essentially all possible physics gets instantiated somewhere, in some bubble, at some point in the eternal ongoing process of nucleation. Our particular set of constants, the ones that permit stable atoms, long-lived stars, carbon chemistry, and eventually something complicated enough to ask questions about its own existence, occupies one point in that landscape. One configuration among 10 to the 500. If the constants in our universe were chosen randomly from that landscape, and if the vast majority of configurations don't permit complexity, life, or self-aware observers, then our existence is the product of a chain of cosmic luck so improbable it strains the word luck past its normal meaning. The universe didn't select our constants because they're special. We observe them because bubbles with constants like ours are the only ones where observation is possible. The unsuitable bubbles, the vast majority exist, expand, and run their course in permanent sterile silence, observed by no one, remarked upon by nothing. Does that make you feel remarkable or impossibly small? The honest answer might be both, simultaneously, and there's no resolving the tension. We are lucky to live in a bubble where the constants are just right for stars, planets, and morning coffee to exist. In the bubble next door, electrons may be twice as heavy and nothing in it, including mornings, ever existed. But even inside our fortunate bubble, even in this one corner of the multiverse where the physics cooperated, something is quietly and relentlessly shrinking. The portion of reality we can see, and it cannot be stopped. Since Newton, the logic of gravity has been intuitive to the point of feeling obvious. Mass attracts mass. Everything pulls on everything else. The apple falls, the moon orbits, the planets stay in their lanes. And when cosmologists in the 20th century first grappled seriously with the expanding universe, the fact that galaxies are moving away from us in every direction, a discovery confirmed by Edwin Hubble in 1929, the natural expectation followed directly from Newton's framework. The expansion should be slowing down. Gravity, acting across the vast distances between galaxy clusters, should be doing what gravity always does, pulling things back, applying the brakes, decelerating the outward motion that the Big Bang set in motion. The universe might expand forever, slowing gradually over billions of years. Or gravity might eventually win, reversing the expansion and pulling everything back into a final, catastrophic big crunch. Either way, the trajectory was expected to be decelerating. In 1998, two independent research teams destroyed that expectation completely. The Supernova Cosmology Project, led by Saul Perlmutter, and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, were both using Type Ia supernova as what astronomers call standard candles, stellar explosions, whose intrinsic brightness is known well enough that measuring how dim they appear from Earth tells you precisely how far away they are. By comparing those distance measurements against the redshift of the host galaxies, you get a picture of how fast the universe was expanding at different points in its history. What they found was not deceleration. The distant supernovae, the ancient ones, whose light had been traveling for billions of years, were dimmer than they should have been if the expansion were slowing. They were farther away than the decelerating models predicted. The universe wasn't breaking, it was accelerating. The expansion was speeding up. This discovery earned Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011, and it overturned the prevailing cosmological model so thoroughly that the field has been rebuilding its foundations ever since. Something is counteracting gravity on the largest scales. Something is pushing, not pulling. Some form of energy, distributed throughout space itself, is driving the expansion faster with every passing moment. Physicists gave it the name dark energy, which sounds like it was coined by someone who understood both the phenomenon and the limits of their understanding simultaneously. The name means, translated honestly, there is something real here that we cannot identify, cannot characterize, and cannot explain from first principles. It constitutes approximately 68% of the total energy matter content of the universe. It governs the large-scale fate of every galaxy, every cluster, every structure in the cosmos. And we do not know what it is. The analogy is almost too perfect in its absurdity. You're driving down a highway, and you press the brake pedal. Hard. The car accelerates. You check the engine, nothing wrong. You check the fuel full. Every system reads normal. But the car is going faster and faster, and nothing you do changes it. Something is pushing from outside the frame, something you cannot see, touch, or switch off. That is the situation cosmology has been in since 1998. The leading candidate for dark energy is Einstein's cosmological constant, represented by the Greek letter lambda. The history of that constant is one of the more ironic episodes in the history of science. Einstein introduced it in 1917 as a term in his field equations of general relativity, a kind of mathematical counterweight he added to prevent his equations from predicting a dynamic, expanding, or contracting universe. Because at the time, the prevailing assumption was that the cosmos was static and eternal. When Hubble's observations confirmed the universe was expanding, Einstein famously abandoned the cosmological constant, reportedly calling it his greatest blunder. Decades later, the accelerating expansion put lambda back on the table, and the data suggests it was the right term all along. Einstein's blunder turned out to be correct. His correction of the correction was the actual error. But the cosmological constant comes with a problem that keeps theoretical physicists awake at night: quantum field theory. Our best framework for describing the behavior of particles and fields at the smallest scales predicts a value for the energy of empty space. That prediction and the observed value of the cosmological constant agree on almost nothing. The theoretical prediction exceeds the observed value by a factor of 10 to the power of 120, 1 followed by 120 zeros. This is the largest discrepancy between theoretical prediction and experimental measurement in the entire history of physics. Not the largest by a little, the largest by a margin so extreme it doesn't have a comfortable description. Physicists call it the vacuum catastrophe, and it remains entirely unresolved. So the force driving the accelerating expansion, the thing determining the ultimate fate of the cosmos, is not understood. Its leading theoretical explanation disagrees with its observed behavior by 10 to the 120, and it makes up 68% of everything. Dark matter accounts for another 27%, also not directly detected, also understood only through its gravitational effects on visible matter, also a mystery at the level of fundamental identity, which leaves ordinary matter stars, planets, gas, dust, every atom of every element in the periodic table, every human being, every instrument ever built, everything physics has studied in 400 years of science at roughly 5% of the total. We have built an entire discipline called cosmology on the study of 5% of what exists, while the remaining 95% consists of two things we cannot identify, detect directly, or explain from first principles. Calling that a complete model of the universe is a generous interpretation of the word complete. But the consequences of dark energy aren't confined to the question of what it is. What it does is already happening, already measurable, and already irreversible, and it is actively, continuously closing the door on the portion of reality we can ever know. Common sense says that time is on our side. The universe has been around for 13.8 billion years, and in that time, light from increasingly distant regions has been arriving, expanding our view, deepening our surveys, filling in the cosmic map. Better telescopes mean seeing farther. More time means more light arriving from more places. The future, by this logic, is one of ever-growing knowledge. The horizon, we assume, recedes as we advance toward it. The opposite is true, and the mathematics has been unambiguous about this for decades. Because the expansion of the universe is accelerating. Because dark energy is pushing space apart at an ever-increasing rate, galaxies beyond a certain distance are not drifting slowly away while we wait for their light to arrive. They are being carried away faster than light can cross the growing gap between us and them. Any light those galaxies emit today will never reach us. Any light we emit today will never reach them. The cosmological event horizon, the boundary beyond which no future exchange of information is possible, sits at approximately 16 billion light-years from our position. Everything beyond that line is already, in the most physically precise sense, in a different causal universe from ours. And that boundary is not stationary. As dark energy continues driving acceleration, more and more galaxies currently within our reach are being carried past the 16 billion light-year line. Galaxies that today are marginally within the event horizon will eventually slip beyond it. The wall is closing, slowly by human standards imperceptibly across any timescale. Civilization has yet experienced, but measurably, inevitably, and without any mechanism that could reverse it. Research by Lawrence Krauss and Robert Scherer, published in 2007, and subsequent analyses built on their framework, traced this process forward in cosmic time with sobering precision. Within approximately 100 to 150 billion years from now, the overwhelming majority of the galaxies currently visible in our night sky will have crossed the cosmological event horizon. Their light, already stretched by the expansion, will redshift further from visible wavelengths to infrared, from infrared to microwave, from microwave to radio waves too faint and too stretched to detect, and then into a silence that no instrument could distinguish from the silence of empty space. What remains after that transition? The local group, the Milky Way, Andromeda, the Magellanic Clouds, and the few dozen smaller dwarf galaxies gravitationally bound to us, all of them, over billions of years, pulled together by their mutual gravity into a single merged structure. Astronomers have already named the eventual merger of the Milky Way and Andromeda Milkomeda. That merged galaxy, along with the rest of the gravitationally bound local group, will persist as an island in an otherwise empty observable universe. No other galaxies, no other light sources beyond the merged remnant of our immediate neighborhood. Any civilization that exists 2 trillion years from now, assuming the physics permits civilizations to persist that long, will look out at the sky and see darkness. Not the darkness we see, punctuated by billions of visible galaxies. Actual darkness. A void, the local group's merged remnant, surrounded by nothing visible in any direction. They will have no observational evidence that 2 trillion galaxies once existed beyond their horizon. The light will be gone. The signals will have faded below any detectable threshold. The entire cosmic history of large-scale structure, galaxy clusters, the web of filaments threading through the observable universe, all of it erased from the observable record, as completely as if it had never been. The analogy that fits a vast library burning from the outside in. Shelf by shelf, section by section, the outer stacks catch first, then the middle floors, then the inner rooms. A scientist working in the surviving central chamber sees, over time, fewer and fewer shelves. Eventually, only the innermost collection remains a handful of volumes, the contents of the local section, with no indication that the rest ever existed. No scorched remnants, no empty frames where books once stood. Nothing. The catalog that once documented the full collection is gone along with everything it described. That is what dark energy is doing to the observable universe. Not dramatically, not quickly, but with the patient, grinding certainty of a physical law that has been operating since before the first star formed. We are alive and doing astronomy at the single most information-rich moment in the history of this universe. Right now, in the early billions of years after the Big Bang, the cosmos is still young enough that most of its galaxies remain within our event horizon. The evidence is still present. The signals are still arriving. The library is still largely intact. Every decade we delay is a decade closer to the outer shelves catching fire. We complain that the James Webb Space Telescope cost $10 billion. But this is the only moment in the entire history of the universe when astronomy is possible, with a full data set. 2 trillion years from now, the most powerful telescope imaginable would show nothing but an empty dark no galaxies, no reference points, no evidence that the cosmos was ever anything other than a single merged remnant floating alone. $10 billion, in that context, is the best bargain in the history of science. And the final question, the one that cuts deepest, isn't about how dark the universe will eventually become. It's about what waits on the other side of every horizon we've described. Whether the darkness is the last word, or whether there's something or nothing that exists beyond all of it, in a place that no physics we currently possess gives us any right to even ask about. In every culture across the full span of human history, the question has always found an answer. What lies beyond the mountains' other lands? What lies beyond the sea, other continents? What lies beyond the sky, the heavens, the gods, the void, the infinite? The specific answer has changed across centuries and civilizations, but the structure has remained constant. Someone asks what's on the other side, and eventually through exploration, through reason, through myth or mathematics, an answer arrives. Humanity has never been comfortable leaving that question open. We are a species that fills its blanks. We cross the oceans. We send probes past the edge of the solar system. We build instruments to see 13 billion years into the past. The not knowing is always temporary. The answer is always, eventually, coming. Modern physics, for the first time in the history of human inquiry, has returned a different verdict. Not, we don't know yet, not "we haven't looked hard enough." Something categorically different we cannot know. Not as a confession of current limitation, but as a structural feature of reality itself. The information does not exist for us. The laws that govern the universe, the same laws that let us build telescopes, derive equations, and map the cosmic microwave background, are the same laws that prohibit any signal from beyond the causal horizon from ever reaching us. The barrier is not ignorance, it is causality. And causality is not a wall that better engineering will eventually break through. This is a distinction worth sitting with, because it cuts differently than ordinary scientific ignorance. We haven't yet sequenced every genome. We haven't yet mapped the deep ocean floor completely. We haven't sent humans to Mars. These are gaps in knowledge that time and effort and resources will close problems of the not yet variety, where the answer exists, and we simply haven't retrieved it. What lies beyond the cosmological event horizon is not that kind of unknown. It's a different category entirely unknowable in principle, not in practice. The information cannot travel to us because the structure of space-time forbids it. No civilization, no matter how advanced, operating under the physics of this universe, can receive a signal from beyond that boundary. The analogy that clarifies rather than complicates asks what lies north of the North Pole. The question sounds reasonable. It has the grammatical form of a question with an answer, but the geometry of a sphere renders it meaningless. There is no north of north, because north is a direction defined relative to the pole, and at the pole itself, every direction is south. The question contains an assumption the geometry of the surface doesn't support. Similarly, what exists beyond the causal horizon assumes there's a vantage point from which that information could, in principle, be accessed. There isn't. The structure of space-time makes the question unanswerable. Not because we lack the tools, but because the question assumes a relationship between observer and information that the physics of our universe does not permit. This principle is not speculative. It is not a hypothesis under debate. The causal structure of space-time, the fact that events outside an observer's light cone cannot affect that observer, is a direct consequence of Einstein's general theory of relativity, the most precisely tested physical theory in history. It is confirmed not by one experiment, but by every observation of the cosmos ever made. GPS satellites require relativistic corrections to function. Gravitational waves detected by LIGO match the predictions of general relativity to extraordinary precision. The bending of light around massive objects, the time dilation near neutron stars, the orbital decay of binary pulsars, all of it consistent, all of it confirming the same framework that places the causal horizon exactly where it is. The horizon is not a gap in the theory, it is a prediction of the theory. And the theory has never been wrong in any observation we have made. If the limits of our knowledge are written not into our effort or our intelligence or our technology, but directly into the architecture of reality, then the philosophy of science faces a question. It has been slow to confront directly. What does understanding mean when the territory being described is, by definition, outside the reach of any possible observation? This is not a rhetorical flourish. It is an active, unresolved debate at the frontier of theoretical physics. Lee Smolin, the physicist and author, and Paul Steinhardt at Princeton have both argued with force and technical rigor that a theory predicting things which are in principle unobservable cannot be considered scientific in the Popperian sense. Karl Popper's criterion for science is falsifiability. A theory must make predictions that could, at least in principle, be shown to be wrong by observation or experiment. If the other bubble universes of eternal inflation exist in regions forever beyond any causal contact with us, no observation we make here could ever confirm or deny their existence. They are not just currently undetected, they are permanently undetectable. By Popper's standard, a theory that predicts only them is not making a scientific claim. it is making a metaphysical one. Smolin, Steinhardt, and others have pressed this argument hard enough that it has created genuine fractures within theoretical physics. On one side, physicists like Guth, Lindy, and Vilenkin maintain that eternal inflation follows mathematically from well-tested inflationary models. That mathematical inevitability is itself a form of scientific evidence, and that the philosophy of science may need updating to accommodate theories whose implications extend beyond observational reach. On the other side, critics argue that a physics that cannot be tested is a physics that has drifted into something else, something closer to sophisticated storytelling than empirical science. Neither side has won. The debate is ongoing. The journals are full of it. You might want to ask at this point, what is the use of knowing all this? If the horizon is real, if the unknowable regions are truly unknowable, if the debate between the theorists has no observational resolution, why does any of it matter? What are we supposed to do with a map whose edges are marked inaccessible by physical law? The answer is precise, because knowing where you stand is the beginning of every honest inquiry. Because a map that accurately shows the limits of navigable territory is more valuable than a map that pretends the territory extends forever in comfortable detail? Because the alternative, assuming the observable universe, is everything. Treating our 46.5 billion light-year bubble as the full extent of reality. Ignoring what the mathematics keeps insisting about what lies beyond is not optimism. It is a failure of nerve dressed as confidence. The honest map shows the edges, and the edges, in this case, are some of the most important features on the chart. After all of it, after 46.5 billion light-years of observable universe, after 2 trillion cataloged galaxies, after decades of inflationary theory, eternal inflation, string landscape, dark energy, topology searches, and Nobel Prizes, the answer to what lies beyond the observable universe is more than you can imagine, and you will never meet any of it. Science delivering the most honest answer available, even when no one particularly wanted to hear it. But there is one thing science cannot take from us, and it is the most important thing in everything we have just explored. Step back from all the numbers. From the 46.5 billion light-years, the 10 to the 62, the 10 to the 500 vacuum configurations, the 2 trillion galaxies, the 16 billion light-year event horizon closing by degrees. Step back from every equation and every cascade of incomprehensible scale. Look at the full shape of what we have just traced together. A species 300,000 years old, living on a rocky planet, orbiting an ordinary star in the outer arm of one galaxy among 2 trillion, has mapped the causal structure of its own imprisonment with enough precision to know exactly where the walls are, why they exist, and what the mathematics implies about everything beyond them. That is not a failure. That is one of the most extraordinary things any form of matter has ever done. We know enough to know that we know almost nothing, and that paradoxically, stubbornly, beautifully, is one of the greatest achievements of scientific thought in the history of this planet. No current model is complete. Eternal inflation is mathematically compelling and directly unverifiable. The multiverse sits at the precise border between physics and metaphysics, real enough to follow from the equations, untouchable enough to resist every experimental test. Dark energy dominates the universe and defies explanation by a factor of 10 to the 120. The topology of the total universe is unmeasurable from inside our causal bubble. We are standing at the edge of the map. The old cartographers used to write at those edges here, "Be dragons." We have replaced that phrase with something more precise and no less honest. Here be the unreachable, the unknowable, the permanent dark beyond the light we can gather. And that is the right thing for science to write. The truest thing, the boundary is not a defeat. It is the most accurate statement about reality that human minds have ever produced. But a wall is never only a wall. Every hard limit in the history of inquiry has eventually forced the development of new frameworks, new languages, new ways of asking questions that the old vocabulary couldn't form. Newton's mechanics hit a wall, and relativity walked through it. Classical physics hit a wall, and quantum mechanics opened a door no one had seen. The causal horizon may be permanent, or the future may generate questions we currently lack the conceptual vocabulary to even pose questions that reframe the problem in ways that make our current boundary look less like a ceiling and more like a floor. Between all the bubble universes, all the folded topologies, all the eternal inflationary oceans with no shore, one thing remains certain. On this small rocky surface, inside this 46.5 billion light-year sphere of light and history, there are creatures made of atoms forged in long-dead stars, asking questions about the shape of everything, sitting with the discomfort of answers that do not fully satisfy, and finding in that discomfort not despair, but the oldest, most specifically human thing there is, the drive to keep asking. That, by itself, not despite the darkness beyond the horizon, but because of it, is a wonder no less profound than any galaxy we have ever named.